As I mentioned earlier, we can represent different types of data using established coding systems. For example, here's a small piece of the American Standard Code for Information Interchange, or ASCII. ASCII is the encoding of the characters in the English language. It includes not only codes for the uppercase letters of our alphabet, but also codes for the lowercase letters, as well as punctuation and non-printing characters, such as the space and end-of-line characters. Here you can see that the code for capital letter A is 65 in base 10, the code for capital B is 66, and so on. Using this coding scheme, we can represent these characters in a computer by converting their decimal codes to binary. What you see here is a representation of memory in a computer. Every computer has a memory unit, which is an ordered sequence of storage locations, each capable of containing a piece of data or an instruction. Each memory location has a distinct address that we use to store information to it or retrieve information from it, using bits or transistors that can be either off or on. The number of bits in each addressable location varies from one machine to another, and the size of a memory location limits the size of the number it can represent. The main memory unit is called RAM, which stands for Random Access Memory, because we can access any location at random. In addition to RAM, we also have ROM, which stands for Read-Only Memory, that is used to hold the startup instructions for the computer. In general, memory is volatile, which means that we lose all the data in memory when we turn the power to the computer off. However, data contained in ROM is fixed and is not lost when the computer is turned off. Looking at the data in our example here, it's impossible to know what a particular address contains without knowing the context in which it was stored. The data in these addresses could be an instruction, an integer, or part of an image. We can't tell just by looking at it. I happen to know that this data represents characters, so let's decode it. First, we need to convert the binary number in each address location to a decimal number. At the top of the screen in the shaded cells, I've included the binary value of each column. Take a minute and figure out the decimal value of each address, beginning with address 0, the first row under the shaded row at the top of the box.